This is the first part of our series on recurrent neural networks. And in this first section, we're going to introduce the basics, as well as look into some coding examples. And then within later parts of this series, we're going to look at extensions, variations, and different architectures of recurrent neural nets, and more complex application scenarios. So generally, recurrent neural networks are a very interesting topic, as they sort of complement the idea of convolutional neural networks. So we've seen that convolutional neural nets, they shine whenever we're dealing with spatial data sets, in particular, like for example, object recognition images, where we're working with spatial relationships. And recurrent neural networks, they are rooted in the analysis of dynamic data sets like time series data, making predictions about future events, for example, because what they do is they inherit some form of internal state representation of previous decisions made by the framework. And so they do implement some sort of memory, and basically being able to go back in time and use previous decisions and previous states of the system in order to make predictions about the current or upcoming events. And of course, as you might imagine, there's several connections between the two, where both of these architectures brought together can be very fruitful, for example, in the analysis of dynamic image data such as video sequences. Okay, so let's dive right in. So here you see on the left, you see a depiction of a very simple neural network. So we're not talking about deep neural net points at this point. It's really just a basic recurrent neural network where we have a single neuron here within our black box. And so what we have here is some input value or input vector x, a single data point, and then this produces some output value at this sum for this data point, and this is basically computed by our black box here by a function f. And what's the interesting part for the recurrent neural nets is that we have some internal state representation that we output from a black box and directly feedback into the model itself. And to get a better intuition, we can unroll this representation in the following manner. So let's say we have several unrollments already done, and then we have this state vector being fed into our system. And now let's say we're looking at the system at time point t1. Then we have some state h0 being fed into the system, as well as some input vector x being fed into the system. And now what's been done is that we have some computation going on and producing some output at t equals 1. This is our value y here. And now what we also do is we feed the state representation h1 into basically our decision making at time point t equals 2. Yeah, so what we can now do is at t equals 2, we compute y2 based on x, but also based on previous decisions, here represented as our internal representation h1. So in the simplest case, h1 might be y1, so that this output is directly fed into the computations for y2, but it could also be something different, and this is actually based on the architecture, sort of the internal implementation of our black box neuron here. So let's look at the mathematics. So Let's briefly first look at this equation right here. So this is actually the computation for given at a single neuron for a single data point x of t. So what we're going to do is we compute the yt at time point t, and what we use as input, as we've already mentioned and shown in the depiction, is that we take the input value at time point t. So let's say we compute y at t equals 2. Then what we use is we use x at t equals 2, multiply this by some weight, and then we add in the representation h of t minus 1, also multiplied by some weight, and then we add a bias term. So this is actually, if you will, this is the, so f would be some activation function, and there's different activations functions. We're going to make a tutorial about this as well, but let's say a ReLU function or something, sigmoid function, all these being valid sigmoid functions, and then we have the weighted sum of the weights times the values of the input vector plus weights multiplied by our internal state representation x, could be vector 2 plus a bias term. And this in total then leads to the final decision about y at time point t. Okay, so this is the very basic mathematical equation on how to compute an output at the current time step using the data at the current time step plus the previous decisions at previous time steps. So, and as I mentioned, here we've looked at the decision making for a single neuron and a single data point at time point t. Now we can also look at this for a layer of neurons and a batch of data points at time point t. Okay, so let's look at possible implementation of such a recurrent neural net. So what we see here is actually an implementation of our module structure, and in contrast to the previous example where we basically said that the internal mechanism of our recurrent neural network module is basically just a single neuron driven by this activation function f. Now we can set this to for example, having multiple neurons, like 5 neurons, where we feed our input into and then summarize the result. And in this case, this would be a case where the output vector would also be identical to the state vector. So if we unroll this, let's do this for 2 time steps, then we start at x0, and then we move the state, which again is equivalent to the output y0, into and feed this into the next layer here. Okay, so let's look at the implementation of this, and we're going to look at this here in using TensorFlow. Okay, so we import TensorFlow, we import NumPy, and then we define our neural network structure. And so we've set it up that we have 5 neurons, as we've depicted here. And we also design our input vector to be of length 3. Okay, so this is our constants. And then what we do is for x0 and x1, we define TensorFlow placeholders. So this will be float vectors of each individual vector is going to have a length of 3, but here we assign none because the overall will be our x1 and x0 matrix, and we did not yet initialize how large this, how many sample vectors we would like to have. So this is set up as a placeholder with having none right here. Since this information is not yet given. Then we define our weight matrices, and here we initialize our weight matrices based on using random samples from a normal distribution, and we set it up as shapes. So the weights of x will be the number of inputs, so this is 3 times the number of neurons, right? So that since we have 5 neurons here, which will, each neuron will be given the input, so that the weights may differ, of course. Otherwise, it wouldn't make much sense to have 5 different neurons here, or 5 identical neurons here. So this is how we set up our weights for the input vector at these neurons for our time step. And at this, in the same manner, we set up our weights for the state variables h, and this is set up as neurons times neurons. WH is a matrix n neurons by n neurons, and this is because we have our what we do is we feed the decisions at one point per neuron. We feed this as our state into the next module, into each neuron, in order to use this information to be combined with the endpoint when the input at the next time step. So this is a matrix n neurons by n neurons. And then finally we have this bias term, or actually bias vector, and this is a vector of length n neurons. So in order to add a bias to each of the individual neurons per layer. Okay, so now that we've set this up, we can actually do our computation as we've been looking at in our examples before. And so first of all, we can compute y0, which, as I mentioned in our demo example here, is the same as the hidden states h0, and this is computed as the 10h function, TensorFlow 10x function of, and then we do matrix multiplication of x0 and the weights wx plus the bias vector. So this gives us our output values and also provides our hidden state values, and this hidden state values can now be fed into the next step of our recurrent neural network. Again, doing matrix multiplication with this time the weights for the hidden states, and then we add, and this is actually added towards the decision based on the new input variables x1 plus the bias term, and this inserted into the 10h function then delivers the provides the y1, the output at step y1, so at time point t1. So this kind of looks like a feed-forward architecture, but what you can see, would be the main difference is that what you can see per step at x0 or x1, we sort of use the same matrices for here for example for the input data, also WH. So this is actually consistent, that is used across time steps, and that's actually also sort of visualizing or implementing this repetitive structure of the network. Okay, so now the next step that we need to do as we've seen in our tutorial on using TensorFlow, is to call the global variables initializer function in order to have our variables be initialized. And actually, so we store this in init, and then we also define our input vectors, our input data. That's as you can see here. So we prepare our input matrices, and then we actually start our TensorFlow sessions and call init.run, and then we actually have the session run using the dictionary in order to fill the variables x0 and x1, and also in order to return our result values y1 and y0, and store that into y0 values and y1 values. Okay, so that's our first recurrent neural network hello world programming example here. So in this example, we created a recurrent net that had 2 steps. Let's consider a network where we would like to have a significantly larger number of steps. So in this case, it would be pretty inconvenient to have to write all our individual steps like we did here with individual matrices and so on and so forth. So here we can make use of a set of different solutions that TensorFlow offers, and so let's have a look at a few of those options. So one idea, or one way to solve this problem of having arbitrary number of steps for our recurrent net is to use the static RNN function. And in this particular case, this is the case up here, we first define what's here called a basic RNN cell. So this is actually what we've seen before. This would be like a single module here, or now we can call this a single cell. Again, consisting of a certain number of neurons, and then having the output being equivalent to h, or h being equivalent to the output that is then fed into the next cell. So here it's referred to as basic RNN cell, and then we give it the number of units, so that's the number of neurons. And now we can call this by, again, we have to again define our placeholders for our matrices yet, and then but what we can do now, instead of doing the computations ourselves, what we can do now is actually to call RNN static RNN, and then we give this function the basic cell definition, the cell definition that we're about to use, and then we also provide our data matrices. And subsequently, once this is called, it provides the outputs, and that would be the computed values y0 and y1. So the rest of the code is again similar to what we've been looking at already, just that this is a bit more comfortable with respect to computing at each time step. So once we call static RNN and provide the basic cell definition as well as the number of as well as the data matrices, the TensorFlow therefore infers the number of steps and connects these basic cells. However, it would be again very inconvenient having to write all these placeholders if we would again would like to have our network have 50 or 100 or 150 steps. So using static, we would have to define placeholders for each step, Also, it could lead into computational trouble because we would have to predefine, and again, define these placeholder, these variables, and this could lead us to run out of memory pretty quickly. So a solution for this provided by TensorFlow is to use dynamic RNN. And the difference is that dynamic RNN internally uses a while loop, or uses the operation while loop in order to iterate over the basic cell. So again, what we do, we make use of the same definition of our basic cell, but you can see a difference here, that we define our placeholder in a different manner, where we give it the number of steps. In our example so far, we've been working with 2 steps, time 0, time 1. So actually we define this as an array. Again, we do not know how many examples per step we will have, but we define the number of steps, and also we already know the number of inputs. And so this is going to be our placeholder for our input array x. And so now there's a few other options that come with dynamic RNN, but right now we leave it at that, and we actually provide both of these information, the basic cell definition and this array to our function dynamic RNN, and that is actually it. And again, as you can see, later we will get the outputs y0 and y1 from this function call. Now let's look briefly at training recurrent neural nets. We will be discussing the typical way of training a neural network using the backpropagation approach in a different tutorial. Here with recurrent neural nets, since we're tracking time, what we typically use is backpropagation again, but it's called backpropagation through time. And so the trick is to unroll the network along the time axis, as we've done, and as is depicted right here. And then we can actually make use of the traditional backpropagation approach. And again, like with the normal backpropagation approach, we first do a forward pass through the unrolled network in order to compute a cost function based on our outputs with respect to the difference to the outputs that we got labels for. And subsequently, we do a backward path in computing some loss function for these output values. We do a backward pass by actually computing the gradients, and then actually we can again do another forward pass and so on forth to minimize the loss function. Okay, so let's build in a simple implementation of such a recurrent neural net. So we decide to have our recurrent net run over 20 steps. And as input, we give values of length 1. And per cell, you remember in our example case before, we had 5 neurons, a layer of 5 neurons per cell. Now we bring this up to 100. And as an output, we would like to get outputs values of length 1. Okay, and this is something that we're gonna discuss in the next slide, how to approach this, because so again we set it up in similarly to what we've been discussing before. In order to use dynamic RNN, we define this 3-dimensional array where we basically leave leave open the number of input values that we want to feed per time step into our system. But actually, since we already know how many inputs we'll have, how long the input values will be, as well as how many steps we want our recurrent network to run, this is something that we can already give to the system. And then therefore we can define x this way. Similarly, we can define the outputs, and now we can set up our neural network, define our cell structure, giving the number of neurons per layer, as well as the activation function, and then we can feed this into dynamic RNN to get the outputs. However, actually what we would like to have as outputs for y should be not the results of the activation functions applied to the 100 neurons, like 100 values per output as an output vector for y. We would rather have y to be a single value per time step. And a very simple solution for that, without applying an activation function on top of this 100 neuron based layer, we can use the output projection wrapper. And the way this works is that we package our cell into this wrapper class, and this way the wrapper will behave like a normal cell. However, it adds some functionality. In this case, this would be that it adds a fully connected layer on top of, without any activation function, on top of our layer of 100 neurons. So therefore we do not change the basic states of our basic cell. Okay, and therefore these fully connected layers do have the same, or make use of the same weights and biases. Okay, so therefore we can actually wrap and map this to a single output value. And then again, as you can see, the rest of the code basically remains the same. Oh, this is a mistake here. This is good that we look at this. So here this should say cell, not basic cell, right? So this is our definition of cell. Yeah, here we did this right. So this should be cell. Okay. Now we can write the entire model. This is setting up our recurrent neural net using the output projection wrapper class, and then we can define our loss function. And what we do use, like with most regression problems, we use the mean squared error. Right, so this square of the outputs that we already know. I'm sorry, the outputs that we predict minus are already known outputs. And then we can define an optimizer and basically build the whole system up, call the global variables initializer, then define the number of iterations as well as the batch size, so how many samples per batch to train on, and then we can define and start and prepare and run our session. So one more thing on actually this output dimensionality reduction that we should mention is that this wrapper that we've been looking at before, this wrapper approach, is basically pretty simple to apply. However, it's not as efficient as another approach that is provided by TensorFlow. The way this works is depicted in this illustration here. is actually to apply a clever reshaping of our outputs, of our initial outputs of each cell. And basically what you see here is actually the trick. So in the previous step we would have applied a fully connected layer per cell on top of the neuron layer in order to reshape our results to a single output value. However, as I've said, this requires one fully connected layer per cell. Now we can basically, by reshaping our values, we can actually collect the outputs of each cell and then reshape this into array of dimension, batch sizes times n steps. So each individual batch size output is given per cell, and now we can put this together into an output of dimensions batch size of each cell times n steps on the number of cells, and then we can feed this information into a fully connected layer here. Okay, so we basically only, in contrast to the naive previous approach, we only need a single fully connected layer here. And again, then we get our individual output values of the same dimension here, or the same length, the batch sizes times number of n steps as output. So this basically does the transformation from these multiple output values into single output value, and then we can basically distribute that back to the corresponding outputs. Okay, so again, main takeaway here is that instead of having per cell a fully connected layer, we collect our results and feed them into a single fully connected layer. So this is our improvement in efficiency here. And okay, the way this can be implemented is going back to our single, like before we applied this output wrapper approach, going back to the definition of our single basic cell, calling dynamic RNN, and now these results are reshaped and then fed into a single dense, so that means full connected layer, and then we reshape it back into our original output structure, getting a single output per time step. Again, okay, and this is actually replacing the output wrapper approach with this reshaping and stacking. And yeah, as you can see, the rest of the code remains the same. So it gets interesting when we go from doing from the prediction actually to generating values with using a trained RNN. So basically, as we've said, the RNNs of course can be used to make predictions about the future. And having been trained on a particular task, this is very nice, given that we now can feed in some input values and then extrapolate into the future. And this can be applied to different areas and leads to the ability of an RNN to generate futures given some input sequences. So this is where this gets really nice, beyond regression and so on and so forth. Okay, now that we've looked at the basic structure of recurrent neural nets, here we can go deeper and actually look into the architectures of deep recurrent neural nets. And we're gonna just briefly introduce this at the end of this particular seminar. and we will go into deep neural networks and particular architectures and so on and so forth, cell types into following seminars in this series. But let's have a look at an example. So what we've seen before was the recurrent neural network being unfolded over time, having a single cell and then some architecture inside, and then over time giving a state, a value, a vector, and feeding this into the next cell. And this actually, of course, remains an important aspect of the deep recurrent neural networks as well. However, what we now do per time step is to build some layers. So this is over time, and then we have over, say, like a spatial dimension, we build cells to create per time step a deep structure of the recurrent neural network. And okay, so we're gonna, as I mentioned, we're gonna look into how to implement deep recurrent neural nets and specific cases and architectures in the next parts. However, one more thing which is very interesting is that these deep RNNs can be distributed over, say, different GPUs very conveniently. So the way we do this is to build our own cell wrapper, and the specific characteristic of this cell wrapper is that it allows us to, when called, actually forward this to any available GPU and do the calculation, return the results. So this is actually the very convenient part. And our cell wrapper, it takes as input the device and the cell. So device being GPU and the cell is our particular cell definition. And then in particular, what is interesting is the call function, which itself uses any free device and then uses the device and then actually runs the cell, computes the output values of the cell. And okay, so this is how this looks like. This again is the class, the device cell wrapper class. So now in this given example, we would have two GPUs. We would wrap our basic RNN cell with the number of neurons into our device cell wrapper, and then basically here we would call this for all our available devices. And then later we call, in order to connect our RNN cells, we call multi-RNN cell. And then again, we can use dynamic RNN for the connections to be made using our input data X and get the results provided in outputs. Something very, in particular, very, very interesting with recurrent neural nets is this idea of using dropout. So dropout in order to address the problem of overfitting. So overfitting basically means that we kind of, in an extreme case, we might memorize our data. So that means that we can perfectly recover everything that's basically seen during training, but more or less are completely unable to do reasonable predictions on new data. That is formally called unable to generalize, so our model cannot generalize to unseen data. And this is always sort of a trade-off between fixing a reasonable complex but not too complex model to our data in order to be able to sort of abstract from what we've seen during training and being able to apply a model to new data sets. And very interestingly, with neural networks, what works pretty well is to use dropout, which is basically during training, and we can only apply this, of course, during training, to deactivate parts of the network structure, so as to deactivate individual neurons, so on, in layers, and see and still train the model, and do this multiple times, so that we generate individual models that have different, randomly selected different neurons being deactivated, and basically train the model that way, and then from these results basically generate models that are pretty robust, and actually then finally are actually also very able to generalize to novel data sets. So let's look at an implementation to make use of dropout. So first we define the probability of how likely individual elements of a network should be disabled, deactivated. And so here we define our numbers of layers, and now we can build up our sets of cells, RNN cells, and then here we use the dropout wrapper in order to decide, in order to apply dropout to our cells. And so in this code, what's happening is that with a 50% chance, dropout is applied to each layer in order to eliminate inputs per layer. So a specific problem with this particular code is that it applies the dropout to the training as well as the testing. And as I've mentioned, during testing, of course, we do not want to change our network architecture and therefore change the results. So dropout is only something to introduce robustness and create robustness during training, during the training process, learning weights, and we should not apply this during testing. So we basically, since we do not, within our dropout layer, at least for now, we do not have any options to apply, to set this to training. This comma here should be gone, actually, just noticing that. We can change the procedure of our entire code, and so what we do is basically, okay, this again should be gone, is to say we basically, when implementing the whole setup for a model, we basically define a train mode that is given as some argument when the code is called. Say, for example, that we give this as a argument, parameter argument, console argument, and then basically decide on whether we are training the model or calling the model to make predictions. And during training, we use our dropout wrapper to apply dropout, whereas in prediction phase we don't. Okay, so that's actually a very easy workaround for this particular issue. Okay, so this were some basic fundamentals on our recurrent nets, and then very brief introduction to deep recurrent nets. So in particular with deep recurrent nets, as well as with recurrent nets with long time steps, what we have is some challenges, in particular surrounding the problem of vanishing or exploding gradients. And this in particular leads to problems, for example, say that we're looking into text classification. For example, we're doing some review, and we will make a coding example on review, movie review classification, for example, or speech recognition system, speech translation system, where we're actually trying to where we get long input sequences. So in the case of movie reviews, for example, a movie review starting with, okay, I really enjoyed this movie, and then there's a long series of sequence of text that comes afterwards. And the model actually, while integrating all these sequences, would have to go really far back in order to memorize this information or to call on this information. I really like this movie when making the final decision. But given that this has been so early in the recurrent neural network and the network being so long, while doing our backpropagation and so on and so forth, the gradients may vanish to a point, the early gradients, that we would basically forget this information and could not recover it. Same for an example in speech translation, where we would, for example, start with, I've been living in France for over a year, and then we have a lot of text about, I don't know, the weather is so and so and so and so and so and so, and then at some point might like to say, and I really don't speak, and then of course, we would like to recall what's the country, or have I mentioned the country that I'm living in, and then the most likely language that I don't speak or speak would correspond to the country. So in this case, of course, French. But since this is so early in the text sequence, the model would have basically, given this problem of vanishing exploding gradients, would have forgot this information. So that's something. And there's further issues with this, so there need to be some solutions to address this. And actually, a very common solution is the LSTM network structure, that or the GRU structures. And actually, we will look how they are built in our further seminars series, and actually really take a deep look into the architecture and how they work, and look at coding examples as well.